My name is Maria Almhult, and I work as project manager at Lignicity. And the events such as today are presented by a project called Lignin for Future. And it's a collaborative project between the parties RISE, Kristinehamn Municipality, Sting Bioeconomy, and Paper Province, and also engages Nordic Paper. And the project is financed with the help of the EU Structural Funds Program, the Värmland region, and by the project partners. And if you have tips about what you would like to listen to in future events, please let us know. You are more than welcome. You can also follow Lignicity at LinkedIn to be sure that you don't miss any news. But today we're going to listen to Jerk Rönnols from RISE first. So Jerk, great to see that you are with us. Welcome. Present yourself.
Thank you. I'm Jerk Rönnols, as said, from RISE, and I work as a researcher and project manager. Among other things, I am heading the project for craft lignin research in our bioeconomy research program, and I'm a doctor in organic chemistry, and I work in a unit called Smart Materials.
Great, and you will share a presentation with us as well that you have prepared.
Yes, I will. Is it time already?
Yeah, feel free.
Okay, just give me a second.
Yeah, sure. And for everyone watching, if you keep your microphones muted during the webinar, it will help everyone to have the best experience. And you can also on the top of your screen choose between different views. So make sure that you have your microphones muted during the webinar. That is the help for everyone to hear us properly. But yeah, please feel free to go ahead with your presentation.
Thank you very much, and good morning to those of you who are overseas, and good day, or perhaps I will tell you today about our work with. It says the host muted me. Do you hear me, or am I muted?
Now we hear you.
Okay, good.
Yep.
Very good.
I think it was an attempt to mute everyone, so we don't have this disturbance in the background. But
all right.
Yeah. Please, you try.
So, our research work on lignin-based elastomers is the topic for today, how to make and functionalize elastic material from lignin. And this is a field that is rather new to us. We have been working in the lignin game for a long, long time, and in the material sciences as well. But this is a fusion that is sort of untrodden by us before. And I will start out with the acknowledgements in the beginning, so we don't have to rush through it in the end. Because it is very important to point out that much of this work has been done by other people than me. So first and foremost is Xin Wei, who is a master student at KTH, who has been collaborating with us at RISE during the fall and the spring. And it's also Monique Bernardes Figueiredo, who is a doctor in material science and former employee at Bloom, which we'll hear more about later, who started out a lot of this work while she was a visiting researcher at RISE. And also Abhilash Sugunan, my colleague, who is together with me, perhaps the brain behind this. We have also received funding from the Troedssons Forskningsfond for Monique's stay at RISE, and Xin is in part financed by CEO Grafén from Vinnova. And we have also received materials and had discussions with Bloom. And we have also had good collaborations with KTH, who have performed measurements for and together with us, and also participated in discussion. So with that out of the way, what is it that we want to do and why are we doing it? Well, elastomeric materials, I think it's a funny definition from UPAC. They say it's a polymer that displays rubber-like elasticity, sort of implying that everybody knows what rubber-like elasticity is. And well, we kind of do. Like, we find it in various applications, in basketballs, to tires, to the soles of our shoes, and in gaskets, and O-rings, and rubber bands, and also in the flooring of playgrounds, or the ground material, and in many other places. So this is just to illustrate that elastomers are very much abundant and in many different areas of applications. So one could imagine that the market is huge. Rubber is, of course, a natural-based product or bio-based product, to a large extent, but there's always room for improvements, and there are some issues around as well. So I mentioned very early that I work in a unit called Smart Materials, and we sort of define smart in that we want to have materials that are sustainable, preferably bio-based, functional if we can. So they're smart meaning sort of intelligent, and responsive and digital. So this is sort of the arena that we set up for ourselves here with working with elastomeric lignin materials, that we want to tick these boxes. And that's maybe easier said than done. But this work from our side started out with reading this paper from NASCAR's research group, Rigid Oligomers from Lignin in Designing of Tough Self-Healing Elastomers. Seems like a very compelling title to me. What they did was they took lignin, some part of the lignin, one should say, and reacted it. So this here represents the lignin with its functional group pointing out, and it can react with this cross-linker. It's polyethylene glycol diglycosyl ether, a tricky word. It's quite tricky in its abbreviated form as well when it's called PEG, but there you go. They reacted with this and get an elastomer, an elastic material, which looks like this. So these are pictures from their paper, this one. And they say that it's both elastic and that it's self-healing, which is two very interesting properties, and also that it's bio-based. One drawback from their method was that they used only a subset of the lignin. They made an extraction with acetonitrile to get 13% of the lignin, which they then cross-linked. And they hypothesized, or they of course tried with the whole lignin, but they hypothesized that the increase of carboxylic acid groups in this extract gave it beneficial properties in the cross-linking. So we were inspired by this. They had something lignin-based that also had the appealing quality of being self-healing. It was flexible, and they had a very simple process. They mixed the chemicals and heated it up, more or less. Some drawbacks in their method is that it only utilizes a small part of the lignin. They require the use of a catalyst in the reaction and had quite high curing temperature at 160 degrees Celsius. So we hypothesized that carboxylic acid-rich lignin would give a better reaction based on what they had proposed, which would make it possible to use the whole lignin for making materials such like these. And also that it could be possible to add various components to the material to make it A, pressure sensitive, and B, conductive. So this is what we are investigating here. So to start out, a carboxylic acid-rich lignin, well, we were lucky enough to be in contact with the Bloom Biorenewables, who specialize, well, what they specialize in, Justine will be able to tell us later on, but in their process, they can make a very carboxylic acid-rich lignin through their aldehyde-assisted fractionation, as they call it. So they go from lignin here with glycosylic acid, which forms acetals over the beta-O4 bonds, and introduce carboxylic acid groups here. So the resulting lignin has 0.9 millimole of carboxylic acid groups per gram, which is quite a lot compared to lignin, which is usually around 0.1 plus minus a few other decimals there. So this seemed like a very good candidate for trying out the reaction. And try out the reaction we did. So long story short, we mixed this lignin from Bloom, which is a powder, together with this PEG-D, the cross-linker with the tricky name, which is a very viscous liquid. We mixed this and heat it up, and what do we get? Well, more or less on the first shot, we got something very nice. We got a small little disc. You can see there's some air bubbles in it, but okay. And it's also flexible. It's bendable and stretchable, which is really nice. And here you can see a larger version of it, which is also, yeah, you can see how bendable it is. And depending on how we produce it, we can get it in some different qualities. So this larger one also has some air bubbles in it, as you can see. These were made in a solvent-free way. So just mixing this highly viscous liquid with the powder, which is, it's a bit tricky to get it to disperse properly. This one here, which you see overlaying the RISE logotype, is from a solution-based system where we have dissolved everything in dioxane, which gives a much smoother end result. And for reference, you can see what happens when we use craft lignin instead. We get this black thing. You can't really see much more than that is a black circle, but it's black and opaque and very stiff compared to these other flexible ones. So very nice. Quickly, we could achieve a transparent, flexible material. As it turned out in the reaction, we didn't require a catalyst. The reaction occurred spontaneously between the lignin and the crosslinker. And we were also able to lower the curing temperature by 40 degrees to 120 degrees and still get an effective reaction. So that was very nice. We tried out a few different ways of formulating this, including exploring some solvent options. We did explore more than these, but these are the ones which we are sort of continuing with. Without using solvent, just mixing the reagents, the lignin and the crosslinker, we got something transparent, which was self-healing to some extent as well. And it was on the plus side. But on the minus side, it was highly viscous in preparation and difficult to disperse properly. And we also got these bubbles, as you can see up in this one. So this is sort of put on hold for the time being, maybe revisited later. We also played around with using aqueous sodium hydroxide solution, which dissolves the lignin very well and yields actually a self-healing elastomer. This is what you see on the top here. We will be discussing those more in detail later on. It's not as nice. It's opaque and it looks a bit more messy than these transparent ones. But we will continue studying the self-healing properties of this. And we could also use dioxane, as mentioned earlier. It gave us something transparent and very smooth, no air bubbles. It's well dispersed. But for whatever reason, this material is not self-healing. It's flexible and elastic, but it doesn't heal itself. But it's a good system for making composites, which we will also return to very, very soon. So to introduce function, then we say that we want to have something that is not only functioning as a material, as a support or a flexible material, we also want to have it be smart or responsive in some way. So the two tracks we choose to investigate here with adding functional additives was to see if we could make the composite to be conductive and or I should say piezoelectric. So conductive, that is quite obvious what it means to everybody, that it conducts an electrical current. If you put something in on the other one side, current should propagate through it and come out on the other side. Piezoelectricity may be more foreign to some of you, but it's basically means that it's pressure sensitive. So when you press on it, it will generate a current, which is unmeasurable by something else. So to make it conductive, we experimented with introducing reduced graphene oxide, in essence, graphene. And for the piezoelectricity, we introduced barium titanate, which is a good material for that. And how did that go then? Well, it was possible to disperse reduced graphene oxide in dioxane together with the lignin and the PEGD, the crosslinker. So we blended it all together. Dispersing graphene is quite tricky. It requires to have a good system, but actually it worked well in this. And we believe that the lignin particles are somewhat of acting like a surfactant for the graphene itself. So it helps it blending in. And you can see here our SEM images of having no graphene at all, 1% weight percent graphene, 2 weight percent, and 3 weight percent. And it looks, although it looks messy, it's sort of homogeneous, which means that the graphene is well dispersed in there, which is a first interesting result. And then, to make a long story very short, we investigated the conductivity of these, or rather the resistance of these. So here on the y-axis, we have the resistance in kilo ohms. It says thousands very faintly up there. And here we have the graphene content in weight percent. So we made 3 samples with 1, 2, and 3% graphene in it. And we can see that in the case when we have 1% of graphene, we have very high resistance. If we want a conductive material, we want a very low resistance. So at 1%, it is to some extent conductive, but it has a very, very high resistance. But when just adding another % of graphene to it, the resistance drops significantly to, it looks like it's close to 0 here, but it's on this 1000 scale, it's 0.4 thousand, so to say. So 418 ohms, and adding even more graphene reduces it further. So that is very interesting. So we want to be on this bottom end of this graph here. So we can see that adding graphene makes this conductive, and that one could think of a million interesting applications of these, I think. I will leave it to your imaginations for the time being. The other thing we investigated was the piezoelectricity. So we took the same lignin elastomer and blended in barium titanate instead, which is a good agent for introducing piezoelectric material or properties to a material. So in this investigation, where you will see the graphs soon, we have our lignin, it's the yellow thing here, and we apply a mechanical force, or an instrument is applying a mechanical force of 60 newtons once every second. And then we will see, does that generate a current? And what the graph here on the left shows you is that, yes, every time when the force is applied, we see a spike here in the voltage. It's not equal height every time, but it's definitely above, or it's definitely detectable. It's actually quite high in terms of its electric materials. And then it returns, the current returns towards 0, and then when we press again, we see the voltage returning. We have a reference sample here to the right without any barium titanate, and you can see it's almost flat on the ground. You can see some very, very, very faint response just introduced by the machinery itself by doing this. But so we succeeded actually here to make a piezoelectric material by introducing barium titanate. And moving forward, I've been mentioning the self-healing properties a few times now, but what does that actually mean? Well, if we imagine this to be our lignin elastomer material, if we cut it like this, we will of course have 2 different pieces. If we then squeeze the 2 pieces back together again, it will heal by itself without adding any other chemicals or any glues or anything. It will just fuse together as itself. So that is what we're seeing, for example, here. You can still see the cut. So this piece was cut here and then pushed back together. And then Xinyi is pulling these apart again. And what happened in this one actually was that when pulling the second time, it broke at a weaker point on the side here and not where it was initially cut. So when it heals, it is actually very, very strong, and sometimes even stronger than other parts of the material. So this was from the sodium hydroxide pathway. This is from the solvent-free pathway, so it's possible in different ways as well. And yeah, we observe these under some circumstances, and explaining the mechanism of why this occurs is difficult. We have speculative hypotheses at best so far. So this is something that we want to investigate further. And we also tried out if the strength of this was affected by the time spent apart. So if we pull apart the material and let it wait for a while before putting it back together, will the healing be better or worse or similar? So we can see for these bars, so these are 2 modes of preparation. We can look at only at the pink bars. So before cut, we have this strength. After cutting it and putting it right back together, the strength of it is reduced to about half. And after leaving the pieces apart for 2 hours, the strength is sort of the same. After leaving it apart for up to a day or 18 hours, it reduces somewhat, but it still heals to a quite significant amount. And we could also see that the concentration of sodium hydroxide apparently plays a role in how strong these are. So I'm rushing by this, sorry for that, but we can have more discussions on that later. But we can conclude that using this carboxylic acid-rich lignin from Bloom made the formulation process simpler and more efficient compared to what we saw in the literature initially, which yielded elastomers of various qualities where we experimented with the formulations. Graphene was also well dispersed in the matrix and gave a conductive material at 2% loading. We could also see that introducing barium titanate gave a piezoelectric material. And in some formulations, we also got a self-healing elastomer material. Yes, and these images were supposed to illustrate what I just was saying. Okay, I will jump by these potential application slides, which are in some ways very exciting, but we gotta keep track of the time as well. So in future work, we will try to study the self-healing process further to understand what is directing this and what is going on really. And also improved formulations of composites. They were nice and they had the properties we wanted, but there were some air bubbles and not 100% perfect dispersion. So that is something to improve on. Also investigate other potential lignin sources. The Bloom lignin is great, of course, as I've shown you, but there are larger volumes of, for example, kraft lignin out there in the world. Could we improve on that to introduce it in such a process? We don't know yet. Also, exploring application. What can we use these materials for is, of course, the most interesting part. And also investigate alternative curing methods. So the road ahead is well planned, but we never know what comes around the hill. And with that, my presentation is done, and I'd be happy to try and answer any questions that may have arisen from the audience.
Thank you very much, Jerk. And yes, there are questions. And the first one is, how stable are acetals to hydrolysis under neutral and acidic conditions? Will it depend on the length of the carbon chain from acetal to carboxylic group?
Ooh. Well, typically, my organic chemistry background says that under aqueous acidic conditions, you will hydrolyze the acetals. For these, I do not know. Maybe it's Justine is better suited to answer this question.
Yeah, as you said, under acidic aqueous conditions, those acetals are typically not that stable. However, for neutral conditions, they are quite stable. Yeah, I don't know exactly the influence of the chain, the distance, but as a rule of thumb, yeah, they tend to hydrolyze under acidic conditions.
Thank you very much, Justine. And the next question is the use of very toxic solvents warranted in the development of new materials? I think a solvent-free process may be much more advantageous if you think about scaling it up to an industrial scale.
Yeah, that is a good point. Of course, it's much more attractive to go solvent-free, but it depends on how many orders of magnitudes more difficult it is. Perhaps a scale-up scientist could help us in that direction. But yeah, there is obviously a point to be made there. And if we were to pursue an industrial scale dioxane-based system, for example, one would need to consider recirculation and such things. And also evaporating large volumes of solvent is a problem, or energy cost in such systems. So, but we're in early experimentation and development phase. We of course should consider those things as well, but still we can allow us the luxury of exploring different alternatives and optimizing it and making it viable for the future a bit later on.
Thank you. And the next one is, have you evaluated mechanical properties of this new lignin-based material? You did mention some, but...
Yes, we have, not extensively, but to some part. I don't actually have the figures from the top of my head, but there will very soon be a diploma work report on this. If you get back to me, I can try to get Chini to distribute it to have this data.
Great, great. And then a comment is dioxane is super toxic. I'm sure there are less harmful ones.
Yeah.
As a hint.
Yep.
And,
So there's a.
Yeah.
Sorry.
No, continue, Jerk, please.
Yeah, that's working with lignin, as I'm sure many people in the audience knows as well. The solubility is always an issue. You need to be able to dissolve it and your reagent, and also be able to remove it. We explored DMSO, for example, which isn't as toxic, but it's and the reaction works fine, but you can't really get rid of the DMSO in a good way because it has such a low vapor pressure. But I'm sure there are other ways to explore as well.
If I can add something on it, we tried ethanol. It kind of worked as well, and this is a way better solvent, except that the ethanol might react with the epoxy. Mm-hmm. So this can be a problem, but we're also exploring that kind of solvent.
Great, thank you. And if more questions are occurring, please type them in the chat. And also afterwards, when we have listened to also Justine's presentation and taken her questions, we will remain online, but off record, and have a informal chat afterwards. So then you can also ask questions, but continue to type in the chat. And Jerk, perhaps you type your email address also in the chat, then everyone easily can access that. And Justine can do the same later as well. But Justine, thank you for popping in already and helping out with the questions. So you are the next speaker today, and please start to let us know more. Who are you? And thanks again to Jerk, but you're staying online and you are with us till the end as well. Perfect. Thank you, Jerk.
Yes.
Yeah, Justine, thank you. You're sharing. We can see it perfectly well.
Perfect. So, hello everyone. My name is Justine Charmillot. I work as a chemist in Bloom Biorenewables in Lausanne, Switzerland. So I work on the lignin and most precisely on the product development side. And today I will present you a bit of what Bloom is doing and the potential of our lignin for the development of sustainable materials. So first, I would like to talk quickly about Bloom's technology. So we are using a patented technology called aldehyde acid fractionation, as Jerk already mentioned, and this allows us to really separate more efficiently the three biomass components to have a high quality product and to incorporate the lignin, hemicellulose, and cellulose into higher value product. So more in the technical side, how does it work? We have here the lignin in the biomass, and typically this is I would say a typical process, and under harsh conditions, I might know those CC linkages might form, and those are really difficult to break when we want to go to the monomers that are high value molecules. We typically get really low yield, and that's the idea of Bloom, is to use an aldehyde that will incorporate into the lignin structure and those beta-O4, for example, and will then prevent this condensation from happening. And then when we try to do a hydrogenolysis to depolymerize it, we get typically a 10-fold increase in yield. And on top of that, what we have is a direct functionalization of the lignin due to the incorporation of this acetal directly onto the structure. And this opens a wide range of possibility to work with this lignin. So the lignin that we get is typically quite light colored due to the non-condensed structure. We have this functionalization here that we can tune, and we have no smell, no sulfur due to the process that we are using. And the first application that I want to mention that we can do is, of course, use it to form epoxy thermoset materials. So those we can use to do elastomers, coatings, films, adhesives, or smart composites. As it was already mentioned before, we just take the lignin, more specifically this GA lignin, and we take the epoxy crosslinker, and we mix it, heat it, and we have these crosslink materials. Very flexible, still high transparency. And what we can see is that we can tune actually the properties, because we can vary the lignin content, and even at really high lignin content, more than 50 weight %, we still have a good transparency and good performance. So they are not brittle already. They are also thermal and chemically resistant, and we focused on measuring also the non-lignin properties, such as the UV blocking and the antioxidant character of those materials. So here I can show you such examples. So depending on the lignin content, here is the glass transition temperature of typical materials, elastomers, and here is what we can obtain by varying the lignin content. You see this is a wide range, and same for the elongation at break, stress at break, and Young's modulus. We have a wide range to work with, so this allows us to kind of tune the materials depending on the application, and this is an advantage because we can go really high in the lignin content, and also by changing the crosslinker, we can change the property. So something else that we measured is the UV blocking ability, because lignin is known to be to absorb the UV. So we did some materials, some elastomers with this system, and we did the same with another lignin. And when we measured the visible transmittance, we saw, as we can see visually, that the Bloom lignin is really transparent, up to 80% of transmittance, whereas the other lignin material were not. And regarding the ultraviolet, of course, as it contains a high quantity of lignin, all of them are really absorbing the UV. But this change of absorbance between the visible and the ultraviolet is really interesting and could open different applications. We also know that the lignin is usually an antioxidant, so we measured if this activity was maintained after the crosslinking, and indeed all the elastomers that we measured still exhibited a high antioxidant activity. So this was measured by this DPPH assay. DPPH is a free radical, and here we are basically measuring the inhibition of this radical. And yeah, you can see that all of the elastomers made with different lignin content show really high activity, accident activity. And those kind of properties, they were obtained without adding anything to the materials. So you can think that combine this with what you have previously presented, we can have a really interesting material. Then there's another interesting field of application that we can use this lignin for. We'll mention this quickly. It's the surface active, as a surface active molecule. So we are really able to perform emulsions with it, use it as a surfactant, because this lignin can have an amphiphilic character, and we can also play with this functionalization. We were able to have a water-soluble grade of this lignin, and it was shown that the GA lignin is actually, in terms of surface tension reduction, which is what we want for a surfactant. So this is the water-air surface tension. The GA lignin, under certain conditions, they compare to the fossil-based surfactant and also outperform the other lignin-based surfactant. There's something else that we can do from this lignin. It's, of course, depolymerize it. So when we do that, we obtain two different things. First one is, of course, the monomers. So we achieve a high purity and a good yield. We have a good control over the selectivity. We can choose specifically what type of monomers that we want. And so basically those monomers are phenolics compound. And those are valuable molecules that can be integrated in food and fragrance, cosmetics, pharma industries, chemical building blocks, and so on. And the second stream that we have out of this depolymerization is the lignin oligomers. And those are really interesting compound because they have a lignin-like structure, but they have a higher energy density that could allow us to use them as transportation fuels, for example. And also they have a high solubility. This is really different from the lignin itself. And with that, we are able to use them as fossil-based, as replacement for fossil-based polyol for some materials. So mostly polyurethane compound. So we could use them to make a polyurethane foam with a high oligomer content, and also polyurethane elastomers. Also, by varying the oligomer content in those, we can see that we could really shift the properties, but still most of them were falling into the range of elastomeric materials due to the good elongational break and Young modulus. So how do we get to all those materials? We are scaling up our activities. And right now we are using this 20-liter batch reactor for the lignin depolymerization. So we are working at the kilogram scale. Of course, setting up standard operating procedure, quality insurance, and we have a really good control over our process. So to get the monomers, we can selectively control our main product. As you can see here on this graph, each color is representing another monomer, and among the different batches, just by varying the reaction conditions, we could really shift the selectivity. And this shift of selectivity was only done using the same catalyst, but just shifting the reaction condition. We're also, of course, trying to recycle the catalyst. This is under development. And the next step that we're starting now is to switch into a continuous process for the next scale up. So practically, how does it look like? This is what we get out, the lignin oil after the lignin depolymerization, and it contains the monomers as well as the oligomers. So we first separate it by distillation, and this is what we get. So the oligomers look like that. They are much darker than the lignin, and those are the monomers. So as I said, this is a mix of phenolic compound mostly. And what we do is we further distillate them to isolate the different monomers. We can achieve quite a really high purity, up to 99%, and a really good recovery. And that's our main monomer. And this is mostly syringol and guaiacol compound. So with that, we are currently trying to develop commercial applications for all of our products, all of our monomers, with commercial partners. So with that, I would like to thank the whole Bloom team that is doing an amazing job. And of course, thank all our partners, without whom it would be really difficult to carry on all those projects. So thank you very much. And thank you for your attention. I think we have room for questions.
Thank you, Justine, for your presentation. And indeed, there are questions coming in. Have you solved the problem of alkylation with aldehydes taking place on aromatic rings during biomass fractionation?
Sorry, could you repeat the question?
Yeah, sure. And if you press on the chat, you can read it for yourself as well. Sometimes it's easier. I read it out. And have you solved the problem of alkylation with aldehydes taking place on aromatic rings during biomass fractionation?
So we are not really considering it as a real issue. Also, we are using biomass which contains a lot of syringal units. So there is still space for it, but less than with softwood, which has only guaiacol units. So yeah, it's not really a problem for us right now.
Thank you. And the next one, are the oligomeric lignin a residue during the distillation?
So yes, basically after the depolymerization, we have this lignin oil, and we flush out all the volatile compounds, and this is what remains basically. Yeah, exactly. But then we do other distillation, and we have other lignin residues that are dimers that still fly during the first distillation. So yeah, we really have oligomeric compound and then other residues, dimers.
Great, a lot of interest on the topic. So we have many viewers and listeners today. But Justine, if you should send one takeaway to the people, what would you like us to remember tomorrow when they ask us, what did you listen to yesterday?
I would say the possibility of this aldehyde functionalized lignin, because it's really tunable and it allows to make different materials. Also on those elastomers, I think it's a really promising topic. So yeah, I would say this tunable materials.
Great. And Jerk, the same question to you. What do you want us to remember tomorrow from the presentation today?
Well, that we can make elastic materials from lignin of different qualities, and that we can add functionality to them. And we have only just started to explore this space of properties.
But when was the first step made? Is it how long ago is it?
Oh, remembering when things happen in time. Is it 1 year ago or 2 years ago? That's maybe 1.5 years ago or something like that. Great.
And looking into the future, within 5 years, what Justine, do you hope for is in place then, if money is not an issue?
If money is not an issue, I hope that we will have built a plant at Bloom to produce even more lignin. And for specifically on the elastomers, I see the great potential because they can basically go in many fields, from, of course, rubber to food packaging. So I would love to see a product wrapped in those kind of materials.
And Jerk, what would you like to see within 5 years?
Well, I would like to see employment of smart functional materials in a broader way and in many different areas, because I think this is really applicable in many different areas. You could have intelligent shoes that understand how you walk and perhaps even adapt to how you walk, and floors and gaskets in cars that are intelligent and tell you when they're about to break or when they are falling apart and things like that. And that would be very interesting to have.
Would the shoes be the #1 application you would prefer, or do you have another one, Jerk?
Well, I did have 2 sports pictures of my initial things with elastomers, both the basketball and the shoes, and that maybe reflects my own interests more, but maybe that isn't what the world needs the most. One could also imagine for health issues, like we have been discussing concepts of making intelligent floors for hospitals and elderly care. It's a bit far off from where we are right now, but one could imagine to like pinpoint signals and see if somebody has fallen down or things like that. Could perhaps be a more humanitarian way of using it.
Yeah. And Justine, what would you see as the #1 application?
Yeah, I was also thinking of shoe soles in terms of elastomers, and others than that, I still think that the properties of those can still fit the food packaging industry. So this could be a great way to apply those materials.
Great. And in the chat, we have more questions, and please feel encouraged to write more there, anyone who's listening in. And could you briefly outline how the AAF tech is applied to cellulose and hemicellulose?
Yes, so of course it also has an impact on those compounds, and the aldehyde can be integrated into the hemicellulose. And then this is not my main topic, but I'm trying. So this is incorporated, and then we can do a bioplastic with it due to the increased reactivity. So this is something we are working on. We are also trying to further characterize the cellulose, see what advantages we can take out of this. But the hemicellulose is a really important part of bloom plants, yes, to do bioplastics mostly.
Yes, do you want to fill in with something on there?
No, I came up with another question for Justine. In here, we have these aldehydes, which are introduced to the lignin, and we have been mainly discussing the glyoxylic acid.
Yeah.
There, which introduces carboxylic acids, obviously. Is that the main aldehyde that you work with, or do you have others that are better or so?
So right now, our process is mostly using this glyoxylic acid. Yeah, due to the many economical reasons and also the good quality of this lignin and the good monomer yield that it gets. But of course, we tried plenty, actually. I think there's a few papers on this from Jeremy Lutterbauer's laboratory at PFL. And yes, this is the first one that was tried was formaldehyde, but for kind of obvious toxicity safety reason, we moved away from this. And this glyoxylic one is the one that we are currently really trying to develop.
And the question is coming in. What is your lignin sources, like fresh woods, biorefiners, wastes, etc.?
Yeah, ultimately, we would like to go for waste. We are currently trying to investigate the different feedstock, but for now we have beech from suppliers in the region. And yes, we really want to be able to be flexible for the feedstock, because focusing on only one type of wood is also not very sustainable. So that's our plan. And to use waste is also the goal here.
So more investigation.
Yeah.
Good. And Justine, Jerk had a question to you. Do you have any question back to Jerk?
I look forward for continuing the collaboration, because I think that what you're doing is really interesting and we are learning so much. But no, right now I have nothing that comes in mind.
I agree. I just want to say.
Yeah. Thank you. And I have no more questions in the chat, so I will say thank you again for taking your time to speak today, and for everyone logging on live to listen to the presentations. And yes, we have recorded, so the recording will be available in a short future online, both on YouTube and on lignocity.se, and everyone who's been registered will receive a link directly to the recording as well. So with that said, thank you for today's webinar.